Welcome to qnawire.
Right, so in this case what we want to do is solve that the gradient of the function r to the n is going to be equal to n times rn to the minus 2 times the unit vector of r. I'm going to label r vector because you know the notation in your homework you can put it as boldface, but right here I'm just going to use an arrow to signify the vector. So whenever we have the gradient of a function, essentially what we are doing is that the gradient of any function f is equal to I times, where I is the unit vector, the partial of f with respect to x, plus j unit vector partial of f with respect to y, plus k unit vector partial of f with respect to z. So if we write down the gradient of r to the n, what we're going to find is that this is equal to I times the partial derivative of r to the n with respect to x, plus j times partial derivative of r to the n with respect to y, plus k times partial derivative of r to the n with respect to z. Now let's recall that the definition for the vector r is equal to x times I plus y times j plus z times k, where x, y, and z is just going to give us the the coefficients corresponding to the x, y, and z components of the r vector. We also know that r magnitude is equal to the square root of x squared plus y squared plus z squared. Thus, r squared is going to be equal to x squared plus y squared plus z squared. Now, what we want to do is, first of all, let's take the derivatives over here in our gradient of r to the n, and then we're going to use this relationship in order to find what is the gradient of r with respect to x, y, and z respectively. So over here, what we are going to find is I times n times r to the n to the minus 1 times the partial derivative of r with respect to x. Here I just apply chain rule, plus j times the same thing, n times r n to the minus 1 partial derivative of r with respect to y, plus k times n times r to the n to the minus 1 partial derivative of r with respect to z. So with this, what I'm going to do is I need to find each of these fellas over here in order to get my expression. So what I'm going to do is take the derivative of r squared with respect to x and see what happens. So the derivative of r squared with respect to x is equal to 2 times r, the derivative of r with respect to x. And this needs to be equal to 2x. From here, we know that we can cancel 2 and 2 over here, and we get that the partial derivative of r with respect to x would be equal to x divided by r. We can repeat the same procedure with the other three coordinates with respect to y and with respect to z, and what you're going to find is that the partial derivative of r with respect to y is equal to y divided by r, and that the partial derivative of r with respect to z is equal to z with respect to r. Sorry, z divided by r. So now what we are going to get is, let's factorize the n to the minus 1 factor of each of the components, and we get that the gradient of r to the n is equal to n times r n to the minus 1 times, in the I direction, the partial derivative of r with respect to x. But what is that? X divided by r, plus j times the partial derivative of r with respect to y, but that is y divided by r. And finally, in the k, we're going to get z divided by r. We can again factorize the 1 over r over here, and we get n times r n to the minus 1 divided by r, times I times x plus j in y plus k in z. And now let's just identify this section as the r vector, the direction that we defined earlier. So this is nothing but my vector r over here. And over here, what happens is I can take the r in the denominator, plug it into the exponent, and we get n times r n to the minus 2 times r as a vector. And with that, we are done with the procedure. Thank you very much and have a good one.